third episode of our continuously growing series of YouTube live talks about the ATLAS experiment and everything connected to the research we do at ATLAS. My name is Sascha Mehlhase. I'm a particle physicist at the ATLAS experiment. For tonight's talk, we'll collect questions in the live chat in YouTube, and we'll ask them to our speaker in a question and answer session after the talk. So make sure you put all your questions into the live chat and we'll pick them up from there. So now I'm very happy to present today's speaker, Professor Daniela Bortoletto of University of Oxford, and also an experimental particle physicist of the ATLAS collaboration. Her recent research is focusing on studies of Higgs boson properties and searching for new physics with the ATLAS detector at the LHC. And she also plays an important role in the development of instrumentation for particle detection, which also brings us to today's topic of the talk, a journey into the ATLAS experiment and how elementary particles are detected. So with this, I hand over to Daniela for today's talk in our YouTube live talk series.
Good evening, everybody. Can you hear me well? Yes? Okay, so in this presentation, I would like to take you through a journey. I hope that you see my marker here, into the ATLAS experiment, how elementary particles are detected. So we are going to go to see how we see particles in this huge detector and how can we use this huge detector in order to discover a new particle like the Higgs boson. So, but what is an elementary particle? So if you look inside matter, you will see, for example, with a microscope, you can see cells. So these are actually onion cells, and that have a dimension in this direction of about 40 micron. And then if you go even deeper, and if you use a scanning electron microscope, you can also see, for example, atoms in this environment, and which have a dimension of 10 to the minus 10 meter, really a very small number. And then if you go even deeper and you use a super microscope like the LHC, an accelerator like the LHC, you can see what there is inside the atom and inside the nuclei, and you can see what is inside the proton, which is a dimension of 10 to the minus 15 meter, which is about 100,000 times smaller than an atom. And at least with the accelerators that we have until now, the particles that we see inside the protons, the quarks, and also the electrons, seems like they are point-like. They have a dimension of less than 10 to the minus 18 meter, very, very tiny. But what is an elementary particle? Sometimes we also call them fundamental particle, which indicates already that perhaps we don't really know what they are, or we don't know really, we don't have a good definition for them. So sometimes we define them as because of quantum mechanics, we define them as a quantum excitation of a field, or we define as, when we measure them, as a collapse wave function, or if string theory is true, they could be like a small string. So, or if you are looking at the definition that is very mathematical, you could say that they are the simplest objects that can be shifted, rotated, and boosted. And but another very practical definition is what we measure in our detector, which I will use for most of my talk. So when we are dealing with elementary particle, we have to use quantum field theory, which is a theory that combines together quantum mechanics and relativity. And so in this theory, for example, we can explain, that energy and matter are equivalent. This theory explains the existence of antiparticle and the duality between particle and fields, and also that forces and interaction are mediated by the exchange of particle. As you can see this graph here, which is called a Feynman graph because it was invented by Richard Feynman. And also another very interesting consequence of quantum field theory is that the vacuum is actually very interesting. The vacuum is continually changing because particle and antiparticle can pop in and out of the vacuum as much as they respect Heisenberg indetermination principles that for a very tiny amount of time. So if you look at the component of the standard model, this is it. So this is the periodic table of the standard model. It's the genetic code of subnuclear physics. And you can see that you have particles like the quarks, you have particles like the leptons, and these are spin 1/2 particles, they are matter particles. Then you have spin 1 particles, that's the force particles, the particles that exchange the interaction. And then you have the spin 0 particles, the Higgs boson, very special particle, neither a matter particle nor a force particle. And the particle, if you see here, are divided in generation. And actually, the first generation is very important because all of matter around us consists of a particle from the first generation, up, down, quark, electron, and neutrinos, okay? And so we don't see the quark per se separately because we see the quark only in bound state, and we call this bound state hadrons. And the Large Hadron Collider stands because you are colliding hadrons, you are colliding 2 protons, okay, and you're colliding protons. And these protons are made up of 2 up and 1 quark and a lot of mess inside it. A lot of gluon, particle and antiparticle are in the protons, okay? And the other particles, the particle of the other generation, are created, for example, in accelerator or in the cosmos or the LHC. But you need energy to create now, but they existed in the early universe. So then you have the force particle, and you have 4 forces that we know in nature, 4 fundamental forces. One is gravity that bounds, the solar system. And we think that gravity is mediated by a particle called the graviton. I have a question mark there because we don't have yet a quantum field theory of gravity. And so there is still a question mark with the graviton. Then you have electromagnetism, which is interactions that binds together, for example, electrons in atoms, okay? And is mediated by a particle, which is called the photon, which is massless. And then you have the strong interaction, which really glue, if you want, the quarks together into protons and neutrons and nuclei, and is mediated by the gluon, which is a particle that carry a color charge, and the quarks also carry this color charge. And then you have the weak interaction that is very feeble, but very important to us as human beings. It's responsible of the fusion inside the sun and give us the energy that keeps the Earth going, let's say. And is mediated by very massive particles, which are called the W+, the W-, and the Z0. So here is again the standard model. So now we know the matter particle and we know the interaction particle. And the quarks carry color, carry charge. And so they interact by the strong interaction, the electromagnetic interaction, and the weak interaction. The charged leptons, like the electron, interacts only, they carry electromagnetic charge, so they interact only by the electromagnetic force and the weak interaction. And while the neutrino are chargeless and they're neutral particle, they don't carry any color, and so they interact only via the weak interaction. And that's why neutrinos can cross the whole Earth without interacting much. And then you have the Higgs boson, and this is really this spinless particle, the first spinless fundamental particle found, is a particle that holds. Is a pyramid, is a pylon on which the standard model stands. Without it, the standard model will collapse. And we searched for the Higgs boson for almost 60 years, and we finally found it in 2012 in CMS and in ATLAS. And Françoise Englert and Peter Higgs got the Nobel Prize for this discovery in 2013, a very major discovery. The Large Hadron Collider was really a machine that was built to find the Higgs boson. It's hosted in a 27-kilometer circumference. Here, you see the Lake Geneva Airport, and it's about 100 meters underground. And it's a machine that explores distances of the order of 10 to the minus 18 meters. It operates very cold at 1.9 degree Kelvins. That is cold as an outer space, which has a temperature of about 3 degree Kelvins, so minus 270 degrees Celsius. And reaches the highest energy ever achieved in the world. I mean, 13 trillion electron volt, which correspond to a temperature that is hotter than the center of the sun, which reaches a temperature of about 15 million kelvins. And it recreates condition when the universe was a billionth of a second old. So very impressive machine. So the machine, the experiment are located in a cavern, underground cavern, and there are 4 caverns around the circumference of the Large Hadron Collider. And we have, and here is a cavern that hosts the ATLAS experiment, the experiment that we are trying to go in this journey, okay? So here is a picture of ATLAS. You see that is a magnificent experiment. Here is the size of a human being inside ATLAS. It's really amazing. It has the size of it's a camera, if you want, of the size of a cathedral. It's sort of a half of the size of Notre Dame Cathedral in Paris. It has a diameter of 25 meters. It has a length of 45 meters. It has a weight of about 7,000 tons, and it takes a picture every 25 nanoseconds. Really impressive. So how do you find the Higgs boson? So I told you already that at the LHC, you're having beams of protons that are circulating at almost the speed of light, and they are colliding head-on. And so we saw other things about the Higgs, the proton that we were watching before. Sorry, I'm having some trouble here. So it's a proton, I told you already that you have the quark inside and you have the gluon inside. And then you, from time to time, when these proton collide with each other, you will produce a Higgs boson. So here is when you produce a Higgs boson, okay? And then the Higgs boson really live very, very short amount of time. So we don't see the Higgs boson per se in our experiment. But what happens is that the Higgs boson will decay, for example, into 2 Z bosons, the quanta of the weak interactions that I just introduced before. And then this particle will decay into electrons and positrons, the antiparticle of the electron, and mu plus and mu minus. And that are the particles that we will see in ATLAS. So this is really quite amazing, let's say. And I show you one event, but again, in practice, in every bunch that we have at the LHC, we have about 10 to the 11 proton, like almost a trillion protons per bunch. And we have about 3,000 bunches per beam crossing every 25 nanoseconds. So there are a lot of these interactions. In most of them, the Higgs boson will not be produced, but sometimes will be produced. And so what we record then are, 4 electrons for muon, 2 electron and 2 muon events. And from this, as time go by, we saw an excess of event in this region here, which has a mass of 125 GeV over the background that is in red here, okay? So you see the background in red, and you see this region here over the background. And here is the area that at the end we find consistent with the Higgs boson. So, but what we found in the detector were the electrons and the muons. So really what we have to do is to look for these bumps when we are looking for a particle, because, for example, a particle like the Higgs boson decays into into a Z boson, and that decays into leptons, and their lifetime is ephemeral. The lifetime of the Higgs is 1.5 10 to the minus 22 seconds. The lifetime of the Z is 3 times 10 to the minus 25 seconds. So these particles live really an infinitesimal amount, okay? And so what you do, you're using really conservation of energy. And what Einstein said is that the energy square of the particle is equal to its mass plus its kinetic energy. And so if the energy and the momentum are conserved, as you learn in any physics classes that you have taken, then by measuring the decay product of the Z, you can find that the energy after the Z decayed was the energy that the Z had before decaying, and the momentum that the Z had before decaying is equal to the momentum of the particle that the Z decayed into. And from this, you can just do a little bit of math and find the mass of the Z, for example, like I'm showing here, which is a very, very, it sticks out like a thumb, it's a very clean resonance. So that's what you are doing, and that in the case of the Higgs, you have to put together your Z and reconstruct the Higgs decay. So the elementary particles that we are really after measuring in our detector are going to be the electron, the muon, the proton, the neutron, pions, kaons, k short, k long, particles that are stable or they live before decaying, okay? So for this particle, we want to determine everything. We want to determine if they're charged, if they're neutral. We want to determine their momentum, their energy, as they're coming from the primary vertex where the proton are colliding or are coming displaced from the primary vertex, and what type of particles. So we want to know everything. We are like detectives, okay? And we also want to detect some other particles which are called jets. And these are stream of particles which are created when you have a quark or a gluon in your detector. So this information allows a reconstruction of what particle was produced and which decay took place. So that is really what we are trying to do. And that's where detectors are coming from. And the definition of the detectors that I like to use come from Klaus Gruppen, who wrote a very nice book about detecting particle, which says every effect of particle or radiation can be used as a working principle for a particle detector. And this already tells you a little bit that once you measure a particle, you also perturb this particle and you cannot measure it perfectly, okay? So here are some examples of interaction. So when you have a charged particle nearby a material, this charged particle will carry some energy and it will lose some energy, this material, and we lose this energy by ionizing, for example, so stripping one electron from the electrons of this atom, for example. A photon coming in a material can produce the electron-positron pairs. Or a photon interacting with material can change its energy and change the energy of the electrons in the material. So the interactions that we are looking for are illustrated here. For example, the electromagnetic interaction of charged particle with matter. The first one is the interaction that I just told you before, the interaction with the atomic electron that gives rise to this ionization, okay? And the incoming particle will lose energy and the atom will be excited or ionized. Then there is also interaction with the atomic nuclei, and this interaction will bend, the particle, and then the particles are deflected, and for example, electron can Bremsstrahlung a photon, okay? And then if the particle velocity in a medium is larger than the velocity of light in that medium, then the particle can emit Cherenkov radiation. And when a particle crosses two material that have different coefficient, then there is a probability that about 1%, that the particle can produce an X-ray. And this is called a transition radiation. Okay, so and all of these interactions that you can have, the particle can have with matter, can be used to detect a particle, for example, a charged particle. If you have an hadron is a particle, a bound state of quarks, for example, like the proton. This is a bit more complex. The hadron can be charged or can be neutral, like the proton is charged, but the neutron is neutral, for example. And so you can have ionization, again, if the particle is charged, for example. But then you can also have the strong interaction. And then the strong interaction is really messy. So you see, at the beginning, you have your particle. It will lose most of the energy by ionization if it's charged. And then you see that it can also lose then the energy also by nuclear processes, like hadron production, nuclear de-excitation, nuclear breakdown, spallation neutrons, and muon and pion decay. So there is really a variety of processes. It's a mess. When you have hadron, you have a messy situation. So what I told you already is that when you have an interaction that allows you to detect particle, it also means that your particles are bent, for example, a little bit by interacting with the nuclei in your material, etc. So you really have to be careful on how you put together your detector. Okay, so assume that so you have your protons going in and out of your screen in these little gray circles that you have here at the center of this strange figure, okay? And that is your beam pipe, where you have the proton are colliding with each other in vacuum, okay? So the first detectors that you put around the beam pipe are detectors that are trying to measure precisely your particle. And these are going to be vertex detectors that measure where the particles is coming from, and trackers, which measures the charge and the momentum by bending the particle in a magnetic field. Okay, and that's why you have a coil here that creates a magnetic field that is usually in the direction of the beams. Okay, so they curl the particle in the direction perpendicular to the beams. And this detector has to be very light, because you don't want to bend your particle. You want to measure the precision, the position very precisely. So they have to be lightweight, low Z materials to measure precisely the position of the particle. Okay. Then around it, you have this electromagnetic calorimeter and the hadronic calorimeter. These are totally different. This detector wants really to absorb the particles that are going through this detector, because they want to measure the total energy of this particle. So really you want to distract the particle, really take all the energy of the particle and measure it all. So for example, in the case of an electromagnetic calorimeter, you are trying to detect electrons and photons mainly. You want a high Z material like lead, for example, to catch all electrons and photon. In the Hadron calorimeter, you want a material that is very high atomic mass material like iron and copper, because you want your hadronic shower to interact as much as possible with this material. So, and then you see that outside everything, you have your muon chambers, because these are still tracking chambers. But at that point, the only particles that reach the muon chambers are going to be the muons, because all the other particles are going to be stopped in the calorimeters. Okay. So, and that is exactly what ATLAS has. Okay, let me just show you a little bit, and then we go a little bit in the detail of how this detector works. Okay. So again, here is a picture of ATLAS. And if you look at a picture of ATLAS, you will have a tracker here inside a solenoid. and then you have your electromagnetic calorimeter, your hadronic calorimeter, and then your muon chambers, okay? And you can see here that, for example, charged particles, like here you have a muon, and here you have the electrons, and here you have a proton. They bent because of the magnetic field created by the solenoid. And you also see that, for example, the photon stop and the electron stop in the electromagnetic calorimeter, while the protons and the neutrons stop in the hadronic calorimeter. And you also see that the photons is a neutral particle, so you can discriminate, for example, a shower in your LM calorimeter, because the photon will not leave the track in the tracker, while the electron is a charged particle. You will ionize the tracker and will leave a charge. And the same between the protons and the neutron. And here are all of the elements. So here we are sitting sort of, so here is a beam pipe in the center, and we are sitting here, you know, sort of in the middle of the ATLAS detector. And here you can see the muon chambers, you know, up here inside the toroidal field of created by these toroids, magnets. And here you find the hadronic calorimeter, and then you find the electromagnetic calorimeter, and then you have the tracker system. Okay, so this is a quick journey, and now we go more in the detail of the journey that we are going to go through this detector. But I want first to make a point, because, you know, obviously you're wondering why we have such a big detector to measure something that is tiny, okay? And really, it's due to the discussions that we had a little bit before. To explore matter at the smallest distances, you need very high energy, because, you know, the wavelength of your wave goes like, you know, is inversely proportional to the momentum of the particle. And so the particles produced in ATLAS are going to be very high momentum and energy. And therefore, to measure their momentum, you need very large magnetic field to bend them. And to measure their energy, we need a sufficient volume to capture all that energy. And here I just would like to give you some numbers to give you some order of magnitude. To absorb 1 TeV electron, you need about 18 centimeters of lead. To absorb a 1 TeV hadron, you need about 2 meters of iron. To measure the momentum of 1 TeV muons, you need a very large value of the magnetic field and a very big lever arm to do your measurement, because the error on the momentum goes like the inverse of this quantity, BL squared. So that's why we build the experiment as it is in ATLAS, okay? So how does a tracking detector work? Okay, I told you already that almost charged particle detectors are based on ionization of some material. And we can have two types of detector. One type of detector, you use a gas, okay? And you have your charged particle, it creates electron-ion pairs, it ionizes the gas, and then this electron can be collected by the anode, and then the signal goes out, okay? Otherwise, you can have a silicon detector. When a charged particle goes in a silicon crystal, it shakes the crystals and it creates electron-hole pairs. And again, you are in an electrical field. In this case, the electrical field goes from top to bottom, and you can collect both the electrons and the holes on the different sides. And you can pattern the silicon detector very finely in order to determine where the particle went through. So the ATLAS Inner Detector, the ATLAS Tracker Detector, has a detector that is a gaseous detector, which is called the TRT. And then it has a silicon strip detector, which is called the SCT, because a silicon semiconductor tracker. And then it has a pixel vertex detector, which is also silicon detector. And then, you know, the pixel detector is closer to the beamline. So the main element of the TRT, which stands for Transition Radiation Tracker, is a tiny gas tube filled by gas, which has this gas tube has a dimension of 4 millimeter, and it has various lengths, okay? And again, to measure precisely the position of the particle. And it is embedded in fibers, which fills the gap between the straw. And so the way that it works is that, you know, your particle, for example, an electrons, okay, will create electron-ion pairs in the gas, and then the electron will be collected, okay? And then, but also because you're changing media here, as I told you, you can emit a transition radiation photon. And by counting how many of these photons, how many of electron pairs you have, you can actually distinguish charged particles from each other. You can distinguish an electron, for example, from a pion, which is quite interesting. But also, as you can see here, you can put this fiber together, and then you see that by seeing where your particle goes through, you can track your particle and see if your particle curls or if your particle goes almost straight. So the highest is the momentum of the particles that you're trying to measure, the straighter it will go, let's say, and the lower momentum particle will curl more according to the lower is the momentum, okay? So anyhow, you get a precision resolution of about 100 micron from this detector. Here it's a little bit the detail of the construction. You can see here your tubes in segments, and then you can put together these segments in barrels. And another thing that you want to do with your detector is that you want to cover the whole area. So you will have also barrel configuration, but then also end cap to catch all your detectors, of all your particles that are created in your interaction as much as possible. So here is your silicon strip detector. The main element here are silicon detector with strips here. And actually you have two detectors, two at the top and two at the bottom. You can see a little bit the one of the bottom because they stick out with each other, because they make a small angle so that you can measure the position in the top and the bottom detector. And then you have two coordinates and you can get your X and Y because you know the angle between the strips. Each of these detectors will have a pitch, have thousands of strips with 80 micron pitch and quite large dimensions, okay, about 12 centimeter times 6 centimeters, okay. And you can see that the strips are read out by these readout chips that are mounted here, and they are connected to the strip by wire bonding, tiny aluminum bonds that you stitch between the detector and the chip, and then all of the information is carried out by these Kapton tapes that connect you with the outside. The SCT barrel was actually built in Oxford, okay, and so so it's a very dear detector. It's a very famous detector here in Oxford. Here is a picture of the innermost barrel of the SCT, which had almost 400 modules, and the outermost barrel, which had about almost 700 modules. So, and these are really big. I mean, each of the modules is about the size of your hands, and you can see that you put them all together and you tile them in such a way that you don't leave any hole, you capture the particles. Then you have the pixel detector, and the pixel is going to have smaller size. So it has a size of about 400 times 50 micron square, and 250 micron times 50 microns, okay? And when you have the pixel, you cannot put the chip at the end of your detector. You have to put it above your detector. And so you connect the readout chip with a tiny band bond. I can show you really a picture of band bond. So the radius of this band bond is about 15 microns. So these are really tiny. So this is really a very difficult process. And that's why we are trying to develop detector where this process doesn't happen, that are called monolithic detector. Here we have a part of the detectors that detects the particle readout built in silicon, and then a silicon readout chip. So we are trying to do together in the readout chip, produce the particle and read it out in the same point, so that we don't have to do this band bonding, which is very expensive. Here is a picture of the module. It contains one big sensor, which is connected with 16 chips that you can see here, and then connected with the hybrid, which then carries, which a hybrid is Kapton and copper, and then it connects the information out through this Kapton lines, and you take the information out according to which pixel fire by this particle. So you get a very precise point of information. So the current ATLAS pixel detector has 3 barrels. You can see them here, 1, 2, and 3, and it has 3 end caps to get the particles that are going forward and backward. And as you can see, it really measures with exquisite precision where the particles are coming from, the vertices. And this is very important when at the LHC we have a lot of multiple interaction. We call them pile-up. Okay, and the pile-up, this event was just collected at the beginning of the detector, but as the detector operated from 2010 to 2011, 2012, and now, the amount of pile-up keeps increasing, okay? And so this is becoming more and more useful, actually. So how do we install the inner detector? So here is ATLAS is a global collaboration, and so part of the detector were built everywhere. So I show you where the SCT was built because it was built in Oxford, okay? But other part of the detector were built in Holland, in the US, everywhere in the world, in Japan, etc. So it's a very global collaboration. So we put all of them together at CERN, and then you can see here, for example, where the SCT was inserted on the TRT, for example. And then it was, you see that there was this installation sort of trolley, that you use actually to move the detector to then to lower it down in the cavern. So here is where it's coming down. I mean, these things gives you a heart attack, I think, when you're thinking that your baby is up there, and then you can see that it's lower down and it's coming closer to the platform, and you can see now that is inserted inside the calorimeter. Okay, so in fact, actually, I should have started with the Muon chamber because that's where we started first, but I just wanted to show you the detector sort of from the inner to the outward, but we will get there. Okay. Here is a pixel detector where they were, sort of looking at the various layer. And again, here is the trolley of the pixel detector, again, lower down in the cavern. And then here is the installation inside the SCT and the TRT. Okay, really, again, an amazing operation. And you see all the cables that are coming out from this detector, a lot of cables, okay. So now let's go to calorimeter. So most of the ATLAS calorimeter are called sampling calorimeters. There are many species of calorimeters, and they consist of plates of different detectors of passive material alternating with sensitive material. And the passive material sort of create the interaction, the decay of the particle, and then the active medium generates the light or the charge that yields the signal inside that we want to get to measure the energy, let's say, of the particle. So if you have an electromagnetic calorimeter, you want to have IZ absorber, like lead, for example, while instead, if you have an hadronic calorimeter, you want to have high atomic mass absorber, like copper or iron. And you can see here that you form a shower, though, by having this structure of the calorimeter. So, for example, if you start with the photon will create a pair of electron-positron pair. Then the electron-positron pair can bram another photon. Then the photon can decay into another electron-hole pairs until you reach a very low energy and you finish your energy and you dump all your energy in ionization. Okay. Here is the configuration of the ATLAS calorimeter. So you will have a barrel region, electromagnetic and hadronic, and then you have extended barrel region, but you also have a sort of end cap region and a forward region in trying to cover the all energy that is coming out as much as possible. So here is a picture of the ATLAS electrocalorimeter that is really a jewel. I really love this detector. I don't work in calorimeter, I work on silicon detector, but this is really a beautiful detector. And you can see here that you have your, I told you that you use a lot of lead here, so you can see the lead here, absorbing plate, and the active material here is actually liquid argon, which is at a temperature of 90 degrees Kelvin. And then you collect your charge generated in the liquid argon, you collected in this copper Kapton tape. And so here is how it works and how the energy generates. So you see you have your incident particle, for example, in this case, an electron, producing a photon, and then you have in the liquid argon, you will create a lot of electron-hole pairs, and then you absorb them in the copper tape, and the shower, until you try to contain the whole shower. And the geometry is such that you try to have like a tower geometry so that you can point and you can determine the location where your photon or your electron coming from. Not very precisely, but you try as much as possible. In the case of the hadronic calorimeter, you have tiles that are built up with 14 millimeter of iron and 3 millimeter of scintillator. So this scintillator is the material that when a particle goes through this material, it emits light. So when the particle loses energy, this material that could be a plastic scintillator, or for example, liquid argon also has some scintillating light also. So it could be like a scintillating a gas or a plastic scintillator, and then you alternate. You see this scintillating tile with iron. And then each of them, you see, you are reading out with these fibers, okay? And you see the fiber coming up. Also, another thing that you see here is that you don't see anything of the detector. The detector is all covered in black tape because you want to protect it from the outside light. You want to collect the energy of the particles that goes through, not the photons in your atmosphere, okay? So you have to tape it all, let's say. And again, you can see the configuration here. You can see a tile here, and then you can see a tile, the finished product of the tile, in the finished product when it's installed in the detector. And here is a picture of, again, you had already some part of the detector here because that's where you start, but you can see the barrel tile calorimeter and the liquid argon calorimeter in place. And that was the status in 2005, actually, for ATLAS. So finally, we are at the outer edge. We are at the Muon Chambers. So the outer layer of ATLAS are the Muon chamber. Here you can see some of the small wheel coming down, okay, and these are in the end cap. And these are also, these are also tracking detectors. So inside them, you will have all small tubes or other configuration with gas that where you have ionization and you will measure the charge. You can see here that the installation, and here is a picture of December 10, 2004, started with actually with the toroid coil. So you start there, and this is a bottom toroid coil, and you absorb there. So the toroid coil, we can create a field because you have current going around here, so the field will go in this direction, okay, inside the toroid, the magnetic field. And that is a magnetic field that bends the muon, and it allows to determine the momentum of the muons. Here are some other picture of the muon chambers that are located. For example, you can see here that you are installing some chambers that are located in between the toroidal coils, okay? And here is again, these are the large wheels, the big wheels, which are really amazing, okay? It's, you know, it's a high engineering project. So now I wanted to show you again some of the events that we show in the original slides. So here is an event where the Higgs decays into 2Z boson, and it decays in 4 muons. So you can see here that you have the tracks in this muon chamber. You can see here the toroid. You have 2 muons here and 2 muons here. And you can also here in the vertex detector see that the muons are coming from the same spot, which is what you need to know that they're coming from the Higgs decay. Here is an event with 2 electrons and 2 muons. Again, you can see the energy of the electrons in the electromagnetic calorimeter, and you can see also the muon chamber lighting up, again, all coming from the same vertex. And again, what you can see here is that we never know if that event was really a Z event, a Higgs event, because we always have background, okay? And so it's only a statistical. We know that the event is likely to be a Higgs event, but we don't know for sure, okay? Here is another event where the Higgs decays into 2 photons. So in this case, you see just the charge in the calorimeter, and you can see that you don't have any charged particle pointing to this cluster of energy in the calorimeter. So these are an evidence for the photon. And you can see here the peak of the 2 photon invariant mass over a large background. And you can see that this is consistent again with the Higgs boson. Here it's another interesting event, because this is an event of the Higgs consistent with the Higgs decaying with BB bar. So here is the Higgs produced with a Z boson, and the Z goes in neutrinos. We don't see neutrinos in our detector. So what we do is we use again energy and momentum conservation. We have the proton-proton going head-on. We don't have any momentum in the transverse plane. So we can measure all of the energy in the transfer plane, and what is missing to get to 0 is going to be your neutrino, okay? And here you see the B jets that are leaving energy in the electromagnetic and the hadronic calorimeter. Here you have a large background, and so what you do, you don't do only the invariant mass, but you use machine learning in order to detect this decay of the Higgs boson above the background. And you see here that this machine learning quantity, which is a boosted decision tree, but there are many, different machine learning tools that you can use, can, in this region here, close to 1 for this variable, where you put all the information, all your measurement of your events, it's consistent with the majority of the events being signal and having very, very small background. And that's what you have to do here in order to get this signal out. Even if the Higgs decays 50% of the time, almost 60% actually, in BB bar. So it's a very large decay, but very, very dirty, let's say, very full of background. And here it's the latest decay of the Higgs that we are not quite observing yet, but we are almost there, is the decay of the Higgs into 2 muons. As you can see here, if we compare, you can see the 2 muons in the muon chamber, and again, coming from the same vertex again. And you can see here, we do the invariant mass of all of the events that we found with 2 muons. And you can see that we have a ratio between what is expected in the standard model and what we observe that is about 1.2, so we observe what is expected in the standard model, but with a huge error, plus or minus 0.6. So we have a 2 sigma, which is way not enough for ATLAS alone to say that we observe this decay mode. But there is another experiment at the LHC, which is called CMS, and they got a little bit of 3 sigma. And the fact that we both see this decay seems to indicate that it is perhaps according to the standard model. So, but again, we usually demand to have 5 sigma, which is really correspond of a probability that of 1 part over more than a million that we could have a fluctuation of the background that mimic the signal to be sure that we have a signal. So 2 sigma for us is not yet a discovery, let's say. Is not even evidence. So what you can see here is that up to now, we have measured a lot of decays of the Higgs boson. And what we see is that the Higgs boson couples more to particles that are more massive. So here is the top quark, which has a mass of 175 GeV, the W and the Z, which have a mass of about 100 GeV, the B quark, the tau, and the muon that has the lightest mass. So you can see that at the moment, everything seems to be in agreement with the standard model. So what is the future? First of all, we need more Higgs event if we want to measure better the coupling of the Higgs, for example, to 2 muons. And we are doing that. We are going to collect many more events by upgrading the machine and by having a collider, which is not called anymore the LHC, will be called the high luminosity LHC, by meaning that we are smashing even more protons with protons together. And we have actually about 200 overlapping interaction for having been crossing. So it's going to be really challenging for the poor vertex detector and the tracker. And so we have to change them. And actually, that's what I'm working on at the moment. I'm working on the new pixel detector, the innermost layer for the vertex detector. And the new tracker, in fact, is going to be all silicon. It's just going to be a silicon pixel detector followed by a silicon strip detector. It's a much bigger pixel system that we had before. It covers a much larger area. It has smaller pixel, 50 by 50 micro, because you have many more tracks density. So you want to have smaller pixel to catch each track in 1 pixel. It will be much lighter mechanical support. So we are building all of this mechanical support in very light carbon fiber. And it will operate at much lower temperature because of radiation damage. The radiation damage is much larger, and so we have to cool the detector much more. In fact, we will have a coolant that is CO2 cooling, and it will be operating, the CO2 liquid will be at minus 55 degrees centigrade, which tells you a little bit of a challenge, okay? Because we are building this detector at room temperature, and then we are cooling this detector. And, for example, in this case, the detector will be made of, a sensor bonded to, to the chip, and then mounted, and then you will have, again, glued to the hybrid. And so you're all having all of this material together that have different index of coefficient of thermal expansion. And if you are not doing your engineering perfectly, you will have discrepancy and you will have stress in the system that can break your system, okay? So the standard system you can see here is a detector actually with 4 chips, which is called a quad module. In Oxford, we are going to assemble this quad module using this robotic system. Just to give you an idea, it's a pick and tool machine that will pick, we will have a stamp, for example, to distribute the glue, as you can see here, on a sensor, and then glue the hybrid to the sensor. And we are checking the material so much that we know exactly how much glue we distribute, about 50 milligram of glues, okay? So everything is done with a precision that is amazing, okay? And as I told you, it must work the mechanical design at minus 55 degrees centigrade. So what can I tell you? These detectors are very complex. They are built by an international collaboration. They are to build them, they are very expensive, and to build them, we need a lot of part of the world to come together. And this is the largest volume detector ever constructed for a particle collider. So building this challenging detector can only be done by the people, the engineers, the technicians, the engineers, the student, the professor, perhaps the professor are almost not the most useful one, okay, but they are useful also, and all of the people coming together to get this detector working, and it's only possible because of the ATLAS collaboration, which is almost 3,000 people, not all in this picture, and almost about 1,000 students. Thank you very much.
Thank you very much, Daniela, for this very nice talk. We actually got quite a few questions, both on YouTube and also what we collected during the day on the Instagram channel. So maybe let's just dive in directly, right? So we have one question, and we'll sort a little bit by starting with detector-related questions first, and then we have some more general questions afterwards. So the first question we have is, if dark matter does not react with ordinary matter, nor is it visible, how are detectors going to detect it?
Well, okay, there are many many different way of detecting dark matter, okay? So in the case of let me go back here perhaps, okay? Oops. Here. So in the case of ATLAS, we can actually see dark matter in a sense by what I was telling you about this missing energy. Okay, so in this event, for example, you have the Z going to neutrino. If if the Z will go to dark matter, you will have exactly the same signature. You will have something missing against something that you observe in your event. So the signature for dark matter in an experiment like ATLAS is very often missing energy seen in the detector, because the lightless supersymmetric, and in the case of if this is due to supersymmetry, the lightless supersymmetric particle will not be seen in your detector and will leave will leave missing energy. So that's how we will see in ATLAS. But there are a variety of ways of seeing dark matter. For example, there are detectors that are usually deep underground, like, for example, xenon 1 ton, where the detection of dark matter is really quite different. It's like the dark matter will sort of interact with these atoms of xenon, and you will observe it in this detector. So this will be called direct detection of dark matter. So there are different detectors and different techniques. Furthermore, honestly, we call it dark matter because we don't know what it is, okay? And so, for example, there are in some theory, like in SUSY, we think that dark matter could be something that has a mass of about, GeV or 100 GeV, something like that, okay? But in other theories, especially for direct detection, in other theories, the dark matter could be extremely light. And so what you will see the coherent effect of dark matter. And you could use, for example, atom interferometer in order to see dark matter. But again, it's not something that we can do in ATLAS, okay? You will build a different experiment to do that, okay? So, and we are really, I think that what I like about the particle physics community is that now we are trying really to have many different experiment, try all to look at dark matter in many different ways to try to pin it down. That is the exploring part of particle physicists. Really, they are looking at the problem and they're trying to build different experiments to look at it. But ATLAS has its way of contributing to this search. And, this missing transverse energy is one of our way.
All right. Then we have another question. How do you shield external influences from the detector?
Well, we are underground, and the way we are really, sort of shielded quite, the cavern is closed by big blocks of material, etc. So we are really underground and shielded. Yeah. So we are quite carefully. And also, we still have perhaps some some particles that come from outside, but it's a pretty small event. And we use them actually to, for example, we use cosmic ray, to take run, in order to test our detectors if everything is working. Yeah. But again, we can measure them very precisely because, we have Muon Chambers. Yeah.
Right. Since you actually talked about the detector being underground and being in a cavern and maybe not so easy to reach, maybe one quick question that goes in that direction. How long did it take to build such a detector?
It builds, it takes decades. And if you take the R&D to get there, it takes really a long time. Yes. In fact, I actually did a part of my career in the US, and the detector that I really built is actually the forward pixel detector for CMS, actually. So I was on the other collaboration. And I started working on the pixel detector for CMS, the one that is installed now in CMS, in 1996. And the detector was installed in July 2010. It was, I remember, it was the last detector to be installed. And I had people, I remember very precisely because I remember that I had colleagues working in the CMS strips that sort of will tell me, we are starting to have the tracking without pixel because you will never be ready, and I was so unhappy, I remember I almost cried, and I was so happy when we beat the expectation and we had the pixel ready. So, every time, what I didn't tell you in this story is what goes wrong also building these detectors, and often you really have setbacks, you have things that you thought that were working and then they stop working. So, there is a lot of, I always think that, to be a particle physicist and to be an experimentalist, any experimentalist, you really have to be really, sort of very determined, because you can get really discouraged sometimes. But again, because the detectors are also underground, you really want to build the safest technologies that you can build. So sometimes our detectors are not the latest state of the art, okay? Because we have to be a bit conservative, because I'm not saying that it's almost to send them to the moon, but it's still, difficult, especially the pixel detector is also buried there. So, you have all the other detector around it. So it's difficult to access it. So it's, so you have to be as careful as possible.
All right. By the way, I think we'll stop sharing your slide sharing so that people can see you better when they. So I think Clara can do that.
Okay, sorry, I forgot completely. I was
That's all fine. That's all fine. But we still have quite a few questions, and then I think it's nice if people can actually see.
Okay, sorry. Yeah.
Right. So we have one, for example, that connects maybe to the various detectors that you just mentioned also. How accurate do your detectors need to be to detect particles? So what's the resolution?
In principle, if you learn what I said about the pixel detector, you would like to have a massless particle that has infinite resolution and infinite, is extremely fast, okay, and so life is a compromise, so your detector is going to be a compromise. You try to do the best as possible. And, it's always, you know, in principle, you know, the pixel detector in terms of precision have a precision of around, you know, less than 10 micron, okay, around 10 micron. So it's really quite good, okay. And again, as I told you, different detector have different precision as you were going, you know, from the innermost, the pixel will be the one that has the best precision in terms of position, and then, you know, the TRT a little bit less, and then, you know, in a sense, in the calorimeter, you don't need so much position precision, but you need more energy precision. So, so it depends, you know, on your detector and what you're trying to measure. What we are trying to do in the future for the future detector is try to measure everything, actually. So the detector of the future, even in the calorimeter, you will try to measure position, energy, and time. Okay, time is becoming a very important quantity in the detector of the future. And for example, at the moment in time, we do maybe around of the order of hundreds of picoseconds. In the future, we want to get to 30 picosecond. Already, actually, for iLumi LHC, we will have some detectors that reach of the order of 30 picoseconds. And again, I cannot go back to my talk, but you remember this talk where I had all of these tracks? If you know if you had the pixel detectors that told you not only you know, with precision the position, but also the time, you will be able to disentangle better this chaos. Okay, so the time becomes important to do this disentanglement. Okay.
That's actually a good point you raised there that connects nicely to another question that we have that now is very similar, but I think it's still worth asking is, how do you say for sure that a particle was from a certain collision and not from another? I mean, keeping in mind that we have so many, I mean, you said the number, right?
Yeah. Again, as I told you, you know, when we build these detectors, actually, we build them assuming that we will have about 20 to 25 collision per bunch crossing. And we were able actually to operate in some bin condition when we went up to 60 collision and even more actually per bunch crossing. We call this pile up. Pixel detectors. I mean, you know, at the end, you know, you are able to connect the particles to that specific interaction. And so you're able to distinguish which interactions are coming from. So the pixel information, the vertex information is very important. And you get also some timing information also from the calorimeter, which is quite precise. So you put together all of the information that you got. Yeah.
All right, then as you already sort of mentioned, it's a quite complex structure, such an experiment, and it not only has the detectors, but it has a lot of other material like mechanical supports, wiring, electronics, and so forth. So there was a question whether all this extra material contaminates the data, and if it does, how do we correct for it?
You take in account every material. So really, and as I said, you know, even when you build, you weight everything so that you would like to have the exact material that you have very, very precisely. So we are not worried so much in the experiments that we have about, well, we are worried about contamination, but not like in some other experiment, like, for example, experiment that look for direct dark matter, okay? So in our experiment, we really try to measure the material, and actually the interactions themselves help us measuring the material. If you recall, I told you that a photon you know, can decay into electron-positron. And you can use this electron-positron actually pair to this, we call them conversion and hadronic conversion in the material to even measure better the material, because often, you know how to say, you know, you start with an idea that you are building a detector and you're really very careful about the materials that you put in, but often you put sometimes a little bit more material than you thought. So what you do, you know, you put whatever you think that is your detector configurations that you've built in your Monte Carlo, and then you use the data itself, like as I told you, photon conversion, hadronic conversion, etc., to measure the material with your detector itself, and then you see, oh, I forgot to put in, this piece of material, and really it's very important that we have this material map, because it's very important for our reconstruction to be as faithful as possible, and in Monte Carlo and data to understand, if we have a new phenomena, for example.
All right. Then we have another question. You answered it in parts. Does the dependence on material in slowing down particles mean that there is a fundamental limit to the size of future particle detectors? Meant in the way that, can they ever be smaller, miniaturized?
It's a good question. I mean, the detectors that we are, there is going to be, we are at the initial step of a new machine that is called the Future Circular Collider, and especially the Future Circular Collider aims at going at 100 TeV, which will be really, going from 13 TeV to 100 TeV, and so all of the detector will be bigger. Okay, as I told you, just you need more material to, to handle your shower, your electron shower, your hadronic shower. So the detector will be bigger and will be more expensive and more complex. So, perhaps we will be able, to use perhaps new material and to be more inventive and to find other solution. For example, one way to keep the detector a bit smaller is to go higher in magnetic field. Okay, if you go higher in magnetic field, for example, you can build a little bit of a smaller detector. I told you, like in the Muon chamber, the quantities that was important was B, the magnetic field, times the distance square. But if you have a much higher B field, you can shrink your detector a little bit. So, but it's not easy to get higher magnetic field, and they cause other problem by working in a high magnetic field. So there are some ideas of trying. You're not simply, just making them bigger. You have some tricks up your sleeve to keep the size a little bit more human size, but they're going to be difficult. For example, in the case, I was looking recently at that for the FCC-HH, we don't have any idea of how to build them, also because of the radiation damage. So in the case of the Illumi LHC, the radiation damage is, we expect about 10 to the 16 particles per centimeter square. For this FCC-HH, we have to go up by a factor of 100. We have to go up to 10 to the 18 particles per centimeter square. We don't even know which material we can put in for any of the detectors, actually. So it's really, I sort of call it the Wild West, because it will be really, exploration, and it will be very interesting, very challenging, also because of the radiation damage.
Indeed, it will be interesting. We have another one that you touched upon, but maybe you can add a few words. There's a question of how do you distinguish between the different types of particles that are detected? So as an example, here it is, how do we find out whether it's a muon or an electron or a photon?
Yeah, our detectors are a little bit like a layer of an onion, let's say, and every layer is sensitive to a different particle. So for example, if you have an electron will give up its energy in the electromagnetic calorimeter. The only particles that reach the muon chamber should be the muons, okay, if everything works well. So it's, so in a sense, every particle gives a different sort of information, yeah. Yeah, in a different part of the detector. Yeah,
it's an interesting puzzle you have to put together then, right?
Yeah.
So then we have maybe one last sort of really detector related question, and then we can move a little bit into more general ones. This is actually quite specific to some extent. Why is the magnetic system placed before the calorimeters in ATLAS and the other way around in CMS?
Very good question. Again, in a sense, in the case of CMS, it's a trade-off. Okay, it's a decision that you take, and the trade-off that the CMS chose. I mean, it was to put, to have it's a larger solenoid ever built. I mean, I think the one of CMS, and it reaches almost 3.8 Tesla, and it was really because the electromagnetic calorimeter from CMS, it's a very expensive homogeneous calorimeter, so it has a tungstenite crystal that are emitting light. You didn't want to spoil the energy of this system with having the solenoid in front. ATLAS decided to have a very thin solenoid and put it before. Yeah. So it's a choice. Mm-hmm. It's a trade-off.
As we often have them, right? As you mentioned before. So now we have a handful of more general questions. You mentioned it before that we actually have several collisions happening at the same time in bunch crossings. And the question here related to that is, how are you able to measure the number of particles that would be collided?
The number of particles that would be collided,
I guess that refers to, as you said before, if we have bunches colliding, there's actually several collisions happening at the same time. And you gave some examples of numbers of how many collisions we have. The question is, how do we get to that number?
Yes, mainly to counting. For example, one way that we have is to count the vertex that we find in the pixel detector. That is one way of counting. We have other way to count that are really more with the beam itself, by counting also, by seeing the luminosities that we have in the beam. So there are, different, depend on what you want to count at which level. So in the detector itself, in the collision, just by counting the vertex that you see in the pixel detector is a good estimate, for example.
And then maybe a related question, as you said before, in the HL-LHC, so the next sort of iteration or the next step after the LHC, pileup will be difficult and will be a challenge. So the question is there any ways to reduce the pileups, to sort of keep it under control to some extent?
Yes, there are methods. For example, instead of having a 25 nanosecond bunch crossing, you could go at a smaller bunch crossing, like 5 nanosecond, etc. But it's also very challenging then, because you should read out your detector faster. So yes, I think, again, this is a compromise that in a sense we know already how it works, and it seems like we will be able to. We have built the detector so that I've done a lot of Monte Carlo. We really have tested the configurations that we will have with the smaller pixel, etc. We expect the same performance or better than we have now. So.
All right, then we had quite a few Higgs-related questions. We won't get to all of them, but maybe we can do one or two in that direction. Let's start. So could there be more Higgs bosons? So you talked about the one that we have already found and that Peter Higgs and François Englert got a Nobel Prize for, but could there be more?
Absolutely.
And is there also, there's a two-part question. Is there also an anti-Higgs boson?
So it's, first the first question. In supersymmetry, actually, we do expect to have 5 Higgs bosons. So we will have the one that we have now, then we will have a charge Higgs bosons, and we have the CP-nib and CP-odd Higgs boson. So we expect to have many more in supersymmetry. So in fact, actually, I worked, at the moment, my groups work mainly on X2BB, but we are also working on X2ZZ. And one of the things that we do in X2ZZ is actually to look look at higher mass to see if we find any other peaks, okay? And at the moment, we have been only able to find limits, so we have not seen them yet. It's almost like we really would like to find something that it doesn't fit the puzzle, but at the moment, everything is fitting the puzzle. So, it's a bit, unfortunately, it seems like everything is matching the standard model at the levels that we have measured up to now. But we are looking for more massive Higgs bosons, I assure you. The antiparticle, well, it's really interesting, this question, because, I in a sense, for example, usually when you have a particle and antiparticle, you have to have something to distinguish the particle and antiparticle. So, for example, you have the positron and the electron, so they have different charge. Okay, already in the neutrinos, because they are neutral particle, the neutrino could be its own antiparticle, okay? And again, it's something that we don't know, because the neutrino could be a Dirac or it could be a Majorana particle. So in a sense, I would say that, in a sense for the Higgs, because it doesn't charge any spin, it doesn't take any charge, it seems like particle and antiparticle should be the same, or should be, it's spin zero. What would be the difference between them? Yeah. So I would say no. I'm not a theorist, so maybe I get it wrong.
But it is indeed an interesting question. There's actually one question related. You mentioned before when you had this animation where the Higgs is created, and then you said that it basically immediately, very, very short time, it disintegrates or decays into two Z bosons, as you had in the example.
Or something else, yeah.
Exactly. But the question was, why do newly created particles, so now it's not necessarily the Higgs, but anything we expect to see in terms of new particles, why do they typically disintegrate so quickly?
Well, it's we don't know. I mean, it's like I'm not. It's really what we have seen that obviously we measure the stable particle and the one that have a small lifetime, etc., because we see them in the detector. So obviously, but there could be, other particles that are stable and we have not yet discovered, for example. So, I'm not saying that all of the particles new particle are going to decay like that, So it's in a sense, it's like, the Higgs could have had a different lifetime, for example, from the standard model. It's, you do measure, and, as an experimentalist, you do measure it and you see what it is, and we measure actually the lifetime by measuring the width of a particle, and the width of the Higgs we have not really measured, but we have limits on it by actually measuring, not directly, because it's too narrow resonance, so we cannot measure. In the case of the Z, it's a broad resonance. We can really measure the width of the Z. But in the case of the Higgs, it's really due to the resolution, the width that we see. I mean, because the width expected in the standard model is about 4 MeV, if I recall. And so, you just measure it, and you see, and we have limits now, and they seem consistent with the standard model, but we could have found something different. Yeah.
All right. So as I said, we had quite a few questions. We can.
For example, there is a lot of effort now in building detector to search for long-lived particles. There is like for example, one of the, sorry, I was just wanted to add this, that this is really a big area of interest, even in ATLAS. I mean, we cannot do much, but again, somehow the way that our tracking works is assuming that everything comes from the interaction point except a few particles, okay? But there could be particles that live a longer time, they travel and then decay, and we are trying even to change the way that we do reconstruction in order to try to find these particles, long-lived particles, and this could be new physics. It could be that we have not found a new physics because our tracking is not working well. We are not tracking or triggering on them, and we have even experiments that are trying to do that by putting, by using the LHC tunnel and putting station in the LHC tunnel to see if there is particles that travel further. Okay, so we don't know. I mean, there could be. I'm not saying that not all of the new particle will decay like that. There could be long-lived particles. That's what I wanted to say.
Exactly. There's many possibilities out there, right?
Yeah.
That we yet have to discover.
Explore.
Exactly. Explore. As I said, we will not get through all the questions, so we'll have 2 closing questions for you, one on the detector side and one more general. First one is, what is your favorite part of the detector, of the ATLAS experiment?
Well, it's a pixel detector and liquid argon. It's really pretty. I've not built it at all, but it's really nice. I love it. Yeah, and it's very elegant. It does a very good measurement. I think the calorimetry for ATLAS, it's a major success actually. Yeah.
I think we could hear that also already in your talk a little bit that you have, but that's great. And then the last question for today is, what do you expect from the future research?
Expecting the future research. Okay, at the moment, I just want to measure more Higgs boson decay mode. Because I started to look for X2BB in an experiment at the Tevatron Collider, which was called CDF, where we were colliding proton and antiproton. So I had like 5 students in CDF looking for X2BB. And then we just discovered it in 2018, and I had some of my students and my postdoc working on it. So I had a lot of fun. Okay, for me, it was really the closing of a big loop. It was really nice. I really would like to measure H2CC, and I think that it's really challenging because it's really difficult to measure charm, to distinguish charm quarks from B quarks, charm jets from B jets. But I do feel like with a very, very, very good pixel detector, we will perhaps do it. And so I'm very excited about that. And I think that we are going to do better with X2 to charm that we think we are. I mean, I always think that we are smarter than we think that we are. And we will try to find, better ways to do it. And if we don't find it at the LHC, part of the future program will be any plus or minus machine, and we should be able for sure to measure X2 charms there. So that is one of the things that I would like to see. I mean, yeah.
All right. So with that, then thank you very much again for this very nice talk and for answering all the questions we had. Thank you very much also to everyone out there listening to our talk and asking these very nice and many questions. Feel free to still post them in the comments to this video. We'll try to get people to address the questions afterwards. And of course, look out for upcoming talks, YouTube live talks of the ATLAS experiment. But for today, I think we reached the end. So thank you very much again, Daniela.
Okay, bye-bye, everybody. Bye.
So see you.
See you. Bye-bye.